Okay, so I think I've gone over why we need to balance equations. And so I need to talk about how to balance equations. So one thing you have to do is look at a chemical equation and looking at the subscripts and the coefficients, figure out how many atoms there are for each element. And that can be a little tricky, at least for me. So let me just kind of go through that as an example here. So for example, we have a chemical equation where we have 3 moles of iron is reacting with 2 moles of oxygen to produce 1 mole of iron oxide. And so one of the things I want to do is just make sure that we can count all the atoms for each element on either side of the arrow. So what you can probably see is that when we're looking at iron here, there is no subscript. So we can assume that it's just, we're really talking about 1 iron atom. And so when you're totally counting numbers and concerning coefficients affecting the number, what you remember is that the subscript is multiplied by the coefficient. So there's 1 iron atom, we multiply by 3. So in this balanced equation, it is represented by 3 iron atoms. Okay, so with oxygen, the subscript is 2. We have 2 moles of it. So on the reactant side of the equation, for oxygen atoms, there are 4 of them there because it's the subscript 2 times the coefficient 2. Now on the product side, we have iron, we have 3 atoms of that. Notice there's no coefficient, so there's only 1 molecule there we're considering. So we have 3 atoms of iron total, and then oxygen, we have 4 atoms. Now the question to ask yourself is this: is this equation balanced? And the way you check if this equation is balanced is you ensure that for each element there is many atoms on the reactant side as there are on the product side. And so what you can see is that for iron there are 3 atoms on each side, and then for oxygen there are 4 atoms on each side. So to me it looks like this equation is balanced. Let's do a little bit more difficult one. Okay, here the counting can be a little bit tricky, at least for me. So let's go ahead and try to count this stuff here. So here we have 1 reactant, calcium hydroxide. So let's count. So we have calcium here, oxygen, and hydrogen. So let's count stuff. So in the formula unit, we have 1 calcium because the subscript is 1, but total we have 3 molecules. So this is 3 calciums total we're considering in the equation. Now how about oxygens? Well, hydroxide has 1 oxygen atom, but we have 2 hydroxides, which is going to be taken 3 times because of the coefficient 3. So to me, it looks it's going to be 1 times 2 times 3, so it should be 6 oxygens. And for similar reason, there should be 6 hydrogens. Okay, the next molecule is called phosphoric acid, if you're curious. And so we have P, O, and H. So let's count these atoms total. So 1 phosphorus and 1 molecule of phosphoric acid taken twice because the coefficient is 2. So we have 2 phosphorus atoms here. How many oxygens? It looks like 4 oxygens times coefficient 2 is 8. How many hydrogens? 3 hydrogens in the subscript of the formula times 2 is 6. Okay, next one on the product side now, we have calcium, phosphorus, and oxygen. So it looks like we're going to have 3 calciums total because we're only having 1 of this molecule, or mole, 1 mole if you want to say. Phosphorus, it looks like there's going to be 2 phosphorus atoms. Oxygens, there's going to be 8. Okay. And so now the final one, water. So we have H and O. So it looks like we're going to have a total of 12 hydrogens here, and it looks like we're going to have a total of 6 oxygens here. Now what we want to do to confirm that this equation is balanced is for each element, check to see that we have as many atoms on the left side of the equation as we do on the right side of the equation. So it looks like we have 3 calciums on either side. It looks like we have 2 phosphoruses on either side. How about oxygens? I'm counting 14 on the reactant side and 14 on the product side. Hydrogens, it looks like we have 12 on the reactant side and 12 on the product side. So this equation is balanced. All right, so we will move on. Okay, so now what we're going to do is practice balancing equations. And so one of the things that I kind of like to do when I'm starting out to balance equations is make a little mini chart where I list out the elements found in all the molecules in the equation, and then I indicate somewhere the total number of atoms for each of the elements on the reactant side and the product side. So I'll show you how to do that in a minute. Now, there's a little bit of strategy involved in balancing equations, and so one of the things you'll learn is if you see an equation and it looks like there may be a lone element on one side of the equation, it could either be the reactant side or the product side. When I say lone element, what I mean by that is the element, the element is found by itself, and the element is not, say, again, represented in another compound. So it just has to be an element by itself, and never you see that element anywhere on another compound on that side of the equation. If you have that case where you have a lone element, that's a good one to balance last. And so there are some other rules here which I'll go over in the next presentation, but I'm going to skip over them for now. But again, I'll go over them in the next presentation. So what I want to do now is just sort of practice balancing equations. So let's do the first one. Okay, so they start out easy and they get a little bit worse as we go through. Okay, so we have H2 plus I2 goes to HI. And if you're curious, HI is hydroiodic acid. Okay, so you may be able to do this in your heads immediately, but let's just do this in sort of a systematic way. And so what I'm going to do is I'm going to write R for reactants, P for products. I'm going to make a little chart here, and I'm going to have H and I. And so now I'm going to count hydrogens and iodines on both the reactant side and the product side of the equation. So we have 2 hydrogens on the reactant side. Looks like we only have 1 hydrogen on the product. With iodine, 2 iodines on the reactant side, 1 on the product. And so what you can see is we don't have a balanced equation yet because we don't have as many atoms of each element on both sides of the equation. That's what we need to do. So what we need to do is adjust the number of molecules by adding coefficients so that we get atoms for each element to balance on either side of the equation. So remember that for the second rule I went over is that if you have a lone element on one side of the equation and you don't see that element represented in, say, another compound, you can balance that last. So we have an example of that here. We have H2 as a lone element, and there's not another compound here with H on the reactant side. We also have that with iodine, but it looks like those are the only 2 elements in this equation, so we have to balance them anyway right now. Okay, so is there a simple way in which we can sort of get atom balance? Now, I'm going to make a mistake. Do not do this. Do not put a 2 here and do not put a 2 there as subscripts. And the reason is when you change the subscripts, what you're doing is basically you're changing the formula for the molecule. And you really cannot do that. So what you have to do is you can only change numbers by adding coefficients. So I'm just going to put a 2 here. So when I do that, now we have 2 hydrogens and we have 2 iodines, and so this now looks like a balanced equation. So we're done with that. Let's move on. Okay, next one. We have tin plus chlorine gives you tin chloride. Okay, we'll make our chart. Okay, so again, we do have elements by themselves, but those are the only ones in this equation, so we're going to have to balance them immediately. And so let's see how we can do that. So let's go ahead and maybe balance. It doesn't matter which one you want to balance first. Let's try balance, or first let's count atoms. I apologize. So we have 1 tin in the reactants and 1 tin in the product. So that is balanced. Now we have 2 chlorines in the reactants and 4 chlorines in the product. So the chlorines are not balanced. So we don't have to mess with the tin balance yet, but let's try to balance chlorines and see how that goes. And so what we can do maybe to balance chlorines is put a 2 here. So we have chlorine with a subscript of 2 times 2 brings us up to 4 chlorines, and we have 4 chlorines there. We did not adjust the tin atoms, and so this looks like a balanced equation, so let's move on. Next one's a little trickier. So we have Fe, which is iron, plus O2 gives you Fe2O3. All right, we'll make our little chart here. Okay, let's do a count of the atoms before we try to balance this. So we have 1 iron in the reactants, we have 2 iron in the products, we have 2 oxygens in the reactants, and we have 3 oxygens in the products. And so you can see right now, as things now stand, the iron atoms are not balanced and the oxygen atoms are not balanced. And so again, we have a case where we do have elements by themselves, but again, the problem is these are the only elements, and so we just probably need to balance them. Okay, so one thing I could do if I wanted to is, let's say if I wanted to balance irons. That looks easy enough, right? So I could put a 2 here if I wanted to, and now the irons are balanced. Now, we have to balance oxygens. Well, here we have 2 oxygens on the left side, 3 oxygens on the right side. So what I'm going to try to do is maybe think of a small number that both 2 and 3 go into evenly, the least common multiple. So the one I can think of is 6. So that may help us. And so that may help us balance the equation. Maybe what we should do is multiply this subscript by some number to give us 6. And let's see what happens there. So if we wanted a total of 6 oxygen atoms and we have 2 in the subscript, we're going to put a coefficient of 3 here. Here we have oxygen 3. So we put a coefficient of 2 there. So now let's recount oxygens. On the left side we have 6. On the right side we have 6. But look what we've done. We've also adjusted the irons. We now have 4 irons in the product side. So while adjusting the oxygens, we threw the irons out of balance, but we can fix that pretty easily. Iron is by itself over here, so all we have to do is just correct this and put a 4 here. And so now we have a total of 4 irons there. And so this, to me, looks like a balanced equation. So we'll move on. Okay. Next one may be a little bit more difficult. Okay, we'll make our chart. So we have calcium, we have oxygen, we have hydrogen, and we have chlorine. Okay, so we have 4 elements to balance. So let's just do an initial count. I'll try to do this more fast. Looks like 1 calcium on either side, that's balanced. 1 chlorine on the left, 2 chlorines on the right. It looks like we have 1 oxygen on the left and 1 on the right, so that's balanced. How about hydrogens? Well, it looks like we have 1 on the left and 2 on the right. So calciums and oxygens are balanced, so we need to balance hydrogens and chlorines. So let's go ahead and balance hydrogens first. Let's see how that goes. So we have 2 hydrogens on the right, 1 hydrogen on the left, so we can put a 2 here. Now we have 2 hydrogens total, so that increases hydrogens to 2. Hydrogens are balanced. Now we're changed the number for chlorine. That is now 2. So the chlorines are balanced. So is this a balanced equation? As far as I can tell, it is. So let's move on. Okay, the next equation is Na, which is sodium plus water, gives you NaOH plus hydrogen gas. Okay, so let's quickly make our chart here. Okay, so before we deal with this equation, let's go ahead and do an atom count. So 1 sodium on the left side of the equation, 1 sodium on the right. Looks like we have 1 oxygen on the left, 1 oxygen on the right. We have 2 hydrogens on the left and 3 hydrogens on the right. Okay, so here we do have a case where we have an element, sodium, that is by itself and it's not involved in other compounds. And there are other elements there we can balance first, so we should leave sodium for last. So sodiums are balanced and oxygens are balanced. So let's balance hydrogen. So this is a little tricky because we have 2 hydrogens here and then we have 3 hydrogens here that are kind of broken up between 2 different compounds. And so here the way I might approach this is I may want to try to see if I can make some adjustments to give me even numbers, and maybe that might make things a little bit easier. So we have 2 hydrogens here, we have 1 here. Let's make this an even number by putting a 2 here. So we have 2 hydrogens there, and so now we have a total of 4 hydrogens. So I'm going to change this here to 4. Now, can we balance the hydrogens here with the 4 we have on the right side? Yes. If we put a 2 there, then we have 4 hydrogen atoms on the reactant side. Now, I probably changed the oxygen count around, so let me recount oxygens. We have 2 oxygens here on the reactant side. We have 2 oxygens here on the product side. The final thing I want to balance is sodium. So we have 2 sodiums here, 1 sodium here. We put 2 there. So it looks to me like this is a balanced equation. So let's move on. And this will be the last one. So we have silver plus H2S, which is hydrogen sulfide, gives you silver sulfide plus water. All right. Okay, so let's set up our chart. So it looks like sulfur, hydrogen, and oxygen. Okay, so let's do our counts really quick. Oxygen, oh, let me put oxygen here. That's fine. Now we're good. So 2 and 1. Okay, so what do we have balanced so far? We have sulfurs balanced and we have hydrogens balanced. And so we need to balance oxygens and silvers. So here again we have sort of a good example where we have elements by themselves on the reactant side and they're not involved in other compounds, so we can balance those last. Now I would say it doesn't really matter which we balance last. We could balance silver or oxygen. So what that points us to right now is the sulfurs are balanced and the hydrogens are balanced. So apparently they're done, so we were now sort of forced to go to the silvers and oxygens. So let's go ahead and balance the oxygens as an example. So we have 2 oxygens here, we have 1 there, so let me put a 2 here. So what I'm going to do is put a 2 there. Now hydrogens, it looks like we threw them out of balance. So we did have 2 hydrogens in here, we now have 4. We have 2 here, so we can rebalance the hydrogens. Let's just go ahead and do that. So we have 4 hydrogens here, 2 hydrogens here. Let's put a 2 here. And so now we're up to 4 hydrogens. So the 4 hydrogens appear to be balanced for the moment. But again, it looks like we threw off the sulfurs. Okay, so now we have 2 sulfurs here, 1 sulfur there. Okay, so can we balance the sulfurs? Sure. So let's go ahead and put a 2 here, and so the sulfurs are balanced. Now, are the silvers balanced? We have 2 silvers here, or excuse me, 4 silvers here. We have Ag2 times 2, 4 silvers here, 1 silver here, and so it looks like we're going to need 4 here. So we're going to change this to 4, and change this to 4. Let me just take a quick look to make sure that this is correctly balanced. Oxygens are balanced, hydrogens are balanced, sulfurs are balanced, and silvers are balanced. All right, looks like we got it. Okay, we will do more difficult equations next time, so thank you for listening.